Okay, we are in paper 4, variant 9702/44, May, June 2025. Usually, no, previously, if it's gravitational field, then it's just a region of space where a test mass experience a force, as I said, but the marking scheme put as force per unit mass. So I ask you to check with your lecturer, right?
Both also can.
Say again,
Okay.
because
Both also can, right?
cannot. If if
Oh,
that if that is what the marking scheme says so, I use the marking scheme from outside, right? Because I have no source from CIE. So your lecturer may have access to CIE lah. So they are, if they use CIE website, then it's more reliable lah. Outside website very rare lah, but they do change the answer. I don't know why lah, right? From the marking scheme that I download from CIE when I was teaching. But for the past few years, it has not happened except recently I've discovered the answer is different from mine. And this one, right? Field is just a region of space where test mass experience a force. Then if it's gravitational field strength, then it's force per unit mass. Okay? So check with your lecturer, but make sure that he didn't use outside source. He used it from CIE. Okay, the gravitational field strength G at a distance x from the center of a uniform spherical planet of mass m is given by the expression G equals Gm over x squared, where G is the gravitational constant and x the distance is greater than the radius of the planet. Describe the pattern of few lines outside the planet that represent the gravitational field to the planet. Right? It's 2 mark. So radial,
few lines are pointing to the center of the planet.
uh, radial, radial is important, and I want worth a mark. And then towards the center of the planet. Explain why a small change in vertical height near the surface of planet G may be assumed to be constant. Right? Since we have gone over it, I just go over with you. The answer, changes in height is very small. Smaller than the radius. We compare the height to the radius. The height near the surface is very small compared to the radius. So few lines are approximately parallel. Okay, they give a alternative answer. Basically, the radius plus the height above the surface is very close to the radius. Huh? That one, very close to the radius, so it doesn't affect G. Assuming that the Earth is a uniform sphere, for Earth, the product Gm is equals to, Gm is given you, determine the value to 3 significant figure for the radius of the Earth. Right? That one is given in the formula sheet. Remember that. Right? So that one is given in the question paper, right? In the previous section. So you just subject, replace your x with your r, take your x square across, take your g down, so r square root of gm over g. Gm is given you, g is 9.81. Right? Look into your data sheet, if you have forgotten. So that is the answer. Calculate the gravitational potential at the Earth's surface. Give a unit for your answer that's given in your formula sheet, or Australian will call it cheat sheet lah, or Canadian will call it cheat sheet. Okay, put the formula, put in the value. GM is given there. R we have calculated. Then use your calculator. The negative sign must be there. Cannot throw it away. Whereas if it's a vector, negative sign doesn't have a meaning unless you tell what direction you are measuring from. Explain why gravitational potential at 2-point mass is always negative. You want to try to explain?
Can say because it's attractive, right?
Yeah. Potential energy is zero. That's important. At infinite separation, gravitational force is attractive. You get 1 mark only, no, like that. Because for both masses, basically, that's the equation for both masses, right? Just different R. So, okay, any comment?
Oh,
State what is meant by two objects being at thermal equilibrium. 2 marks, 2 points. Without looking at your
both
answer.
at the same temperature,
Okay, 1 mark.
both at and no net heat flow in between.
Okay. Same temperature as each other. No net transfer of thermal energy between them. Try to use thermal energy rather than heat. I don't know
Oh
why
yeah.
they don't like heat. In their answer, they don't use heat, they use thermal energy. Follow them, no?
Okay.
Because they are the marker. I'm not the marker. To me, I see no difference. A mass X of ice at 0 degrees Celsius is placed in a beaker containing a mass M of water at Celsius temperature T. The beaker is perfectly insulated, so has negligible heat capacity. After some time, the ice that was added reached thermal equilibrium with the original water in the beaker. Specific heat capacity of fusion of water is L. Specific heat capacity of water is C. Final temperature is theta. Give your expression in terms of sum for all of the x, m, t, theta, L, and C for thermal energy. Right? Have a picture in your mind, or you can sketch on the question paper. That's where your ice is, mass X. There's your temperature T, degrees Celsius. Water have a mass capital M, and you add to the ice, so the final temperature of the mixture is theta. So E1 is the gain by the ice as it melts from 0. Okay, that's simple lah. Right? Mass of ice times L. And then E2, lost by water at its Celsius temperature decrease from T to theta. Right? That mass decrease to that. They use capital X. So we should also follow them capital X. And this is just trying to encourage you to give you confidence. That's why it's very straightforward. E2 equals to MC and MC T minus theta. E3 gained by melted ice at its Celsius temperature reaches from 0 to theta. Right? Melted ice is ice water at 0 degrees Celsius to theta lah. Okay, so there's a rise in temperature lah. Okay, have I done something wrong here? Heat gained by ice. So they use the answer in B to show that the final temperature of theta, the system is given by that. Okay, basically you just heat gain by ice, heat loss by water, right? XL. This one is MC theta. So I think this is something wrong here. There's something wrong here. Okay, happy with that?
Yeah.
Something wrong here lah. Just a correction there. Because it's going from 0. Sorry. Why am I so careless? Okay. I refer to the previous question. Heat gain equals to heat loss. This gain by ice. That's the E3. That's your E1. That's your E2. Then simplify. You want theta, take the theta to this, take the theta, MC theta to the other side. Take XL to this, the other side. So you got MCT minus XL. Then you can take the theta out, right? Take it to the other side, it becomes positive. So it's a XC minus MC plus MC, right? There. Okay, can
Yeah.
state what is meant by ideal gas. Can, without looking at the answer.
Do you guess?
Say again. State what is
Yeah.
meant by an ideal gas.
The product of its pressure and the volume is proportional to the absolute temperature.
Okay. Gas that obey PV is proportional to T at all value of pressure, volume, and temperature, where T is the thermodynamic temperature. Right? That's important. This one is worth a mark.
Oh yeah, thermodynamic temperature.
Right? PV is proportional to T at all values of pressure, volume, and temperature. An ideal gas, pressure is given, density is given. Show that the root mean square speed of the molecule of the gas is approximately there. T is given. Right? In case you have forgotten, if you can remember it, and choose the right formula to use. Okay, the formula. And remember, density is, this is density. And take the square root of this one. Take 3 over nm down. So nm density becomes bottom there lah. And put in your value lah. 3 times pressure and density divided by density. Right? So it's round off to two significant figure lah. Because all the value are in two significant figure only. Any comment? No, Stop me if I'm going too fast. One molecule of gas has a mass of that. Determine the thermodynamic temperature of the gas. What formula do you use?
Half mc square.
Use the kinetic energy formula lor. Or derive lor. Derive that from these two formula. NKT equals to that one there. N and N can cancel off. So you got 1/3 mc square equals KT. PV is the same. N and N can cancel off. So that's why you get this formula. So you want to find T. T is take the K down. Put in your value. There's your M. C, we have obtained it previously. 3, K, get it from a data sheet. 290 Kelvin. Calculate the internal energy. Calculate the internal energy yield of 6 mole of gas. Explain your reasoning. What formula to use?
Internal energy or ideal gas equals to total kinetic energy of product. Wait.
Okay. Potential energy of molecule is 0.
Molecules.
That's our first step. Then internal energy is the total of kinetic energy. N molecules. This kinetic energy of one molecule. This N for N molecules. Then convert it to this one. Replace your N with number of mole times Na, Avogadro's number. And put in your value, half. Number of mole is 6. Avogadro's number. And mass, that's the mass of a gas molecule. And then C square, just what we got previously. Round up to significant figure. 2100 joule. Any comment?
No.
You can expect so far lah. Every year, every option have simple harmonic motion lah. So what is meant by simple harmonic motion? You can remember without looking at your answer.
Simple harmonic motion is
Is
the acceleration proportional to displacement from a fixed point.
Say again.
Motion of an object where the acceleration is proportional to displacement from a fixed point.
You get 1 mark only.
Oh yeah,
Motion
direct
in
towards
which
that point. So always
is directly proportional
and
to
always direct.
displacement. That's the first point. And acceleration is always directed towards the fixed point. That's the second mark. right? Make it
Oh,
clear.
okay.
A small sphere is suspended from a fixed point P by a string, that's a string of negligible mass as shown in figure 4.1. The sphere is given a horizontal displacement and then released. Right? That's where it's released. That's the alternative answer for here lah. Either acceleration is always directed towards a fixed point, or acceleration is always in opposite direction to displacement lah. Either one lah. The sphere is given the small horizontal displacement and is then released. The variation with time of the horizontal velocity v of the sphere is shown in figure 4.2. State 2 times at which the sphere is passing the same direction through the equilibrium position. Yep.
Time.
Yep.
First one is T3. Second one is T5.
Huh? T2 or T6. This is one wavelength lah, or one oscillation, one complete oscillation lah. Or T3 and T7, T3 and T7. Okay.
Oh, okay. Yeah, T2 and
Just
T6.
review the
Okay.
diagram lah. Basically, it is going to move from here back to this one, go back to here, and then come back. This one is going the other direction, right? And come back again. There's one full swing, both in the same direction. So it's basically one period lah. They're both in the same direction. So it's this time there, right? Where is the maximum this velocity time graph, not displacement time graph, but it's the same. Velocity is greatest at the center. Okay, remember, velocity is greatest at this point. One is going the other this way, negative. This way is positive. Okay. Okay, that's why they give you to answer. T2 is here, and T6 here. Right, the one is T3, this alternative answer lah. T3, T7. The time interval between T1 and T6, T1 is here, T6 is here, is 2.2 seconds. Calculate the frequency of oscillation of the pendulum. Sorry, it's a bit hidden there. Let me see whether I can do anything on that. Frequency of oscillation of the sphere. Okay.
0.57.
T6 is one wavelength or one period lah. And this is another quarter lah. Okay, and calculator. And frequency is one of the period. 0.57 hertz. is given in the formula sheet. The sphere in B is undergoing simple harmonic motion. Use your answer part B part 2 and data from figure 4.2 to determine the maximum displacement of the sphere from equilibrium position. Right? That's why we have calculated frequency, and then same as circular motion, where you use radius, just here you use amplitude, right? V naught maximum velocity, x naught is the maximum amplitude, and then omega angular frequency. Right? Or you have forgotten, go to here, put x equals 0. Omega is 2 pi f, right? Frequency, that, right? Calculating omega, x naught, you can read from the graph. Right? That's the x naught, that's your V naught. So x naught is V naught over omega, right? From this equation. V naught from here, V naught from here, right? Don't worry about the negative sign. Divide by 3.57, get this answer. Okay, any comment?
No.
Define electric potential at a point. Okay, so you can remember without looking at your answer.
Work done per unit charge in moving a small moving charge from infinity to a point in electric field.
Work done per unit charge in moving positive. Remember the positive is a
Positive.
right? Positive charge from infinity to the point. You can combine them together, but that's how they give the mark. It's a 2-mark question. An isolate solid metal sphere of radius r is given a positive charge. The potential at the surface of the sphere is 9 times 10 to the power 4 volt. At distance 3r from the center of the sphere, the electric field strength is given there. Determine the electric field strength at the surface of the sphere. Okay, so that is the formula for potential electric field strength. So what is given? This is given. Then they are given 3r. Replace that as 3r. 3r, you square that, it becomes 9r square. And it's given by, okay, 10 minutes time we have to stop already. Right? There's that one there. And then study, these two are the same. Except there's a 9, there's an r here, extra there. Okay. So combine them out. This one there is that one there. And then times your times your 9, take the 9 over there. Take a 9 over there. That can or not? Or do your own way lah. If you cannot see my way. Yeah,
Yeah, about the same.
I just take the 9 over there, that's all. Use this equation. Take the 9 over there. You want electric field at the surface there. So it's 9 times that. You get that. show that the radius of the sphere is 5.0 cm. I can either use electric field. Right? That is given. Right? We are just using this equation now. Except we take the 9 across there, or we have derived it itself here. Right? Electric field strength at the surface. Right? Electric field strength at the surface there. Then there's the equation given for your potential at the surface. Right? There's a difference between this one. You just take R across there, or R across there, ER equals to that. Then replace the E, replace the E with that. So R is just V over E, V over E to get R. Right? Sorry, I tried to squeeze everything together. So V is that, E is that. We want it in cm, so change to cm. Can do your own way, do your own way, as long as you can get the answer. Any comment?
No.
Calculate the charge on the sphere.
C equals Q over V.
No, is that not? You have calculated R already. You have not, you have known that's given. That's given. So take cross multiply, take this one across there. Right? 9 is this one, 9. Or this one, 9. 4 pi epsilon, 8.85. Take from data sheet. And this is radius. Okay. Any comment? Anything not clear? Okay. Use the answer in D part 3 to determine the capacitance of capacitor of the sphere. Go to definition. You calculated the charge on the sphere, potential on the sphere. Okay. C is Q over V. Okay. 5.0, 9 times 10 to the power 4. So I get 5.6 and 10 to the power minus 12 farad. A rectangular coil PQRS. A wire is free to rotate. That's the axis of rotation, as shown in figure 6.1. There's the current in, current out. The coil has QR 5.4, and width PQ, width PQ 2.5, and has 190 turns of wire. The plane of the coil is at an angle of theta. That theta there. In a uniform magnetic field, 5.2 times 10 to the power minus 3 Tesla, the axis XY of the coil is normal to the field. That's the axis. Right? Current in the coil is 1.2 ampere. So now you look at PQ, end view. That's your end view. Calculate the magnitude of the force on side QR. Sorry, yeah, QR. This side there. Right? PILN, N for number of turns. This current, this is the length. So it's 5.2 for the magnetic field strength.
6.4.
0.
Understand the
0.064 Newton.
Yeah.
Right, top. This is your AS work. Now apply to A2. Right. Force and perpendicular distance. No? Force we will calculate. Take one force and perpendicular distance between the forces. So it's F, PQ cos theta. The angle is theta also. 0.64 is the force. And then that length from the question paper. Okay, change it to meter. PQ cos theta. So we get very common. They will ask you to draw graph. So you cannot see the scale, draw the scale properly. No? Put your scale yourself. No? Using the expression of A part 2 sketch on the axis of figure 6.2, a graph to show the variation with torque theta, torque tau with angle theta, values of theta between 0 to 360 degrees, label the axis. Remember, that's the equation that we have
It's a cos graph.
Yeah, it's a cos graph.
Middle at 1.
We were looking at one complete cycle, 360 degrees. One complete cycle. One mark. Label. Right? That is your maximum. That's your minimum. Maximum at 0 and 360 degrees. Minimum at 180 degrees. Okay, we're looking at this point for your third mark. No? Any comment?
So,
You got less than 1 minute. 1 minute. So you got question to ask, you can ask, or you can make any comment.
oh, good.
The coil is now replaced by an identical coil, one on the ferrous core. Suggest you reason how the torque I give you the answer since you anytime you will cut off already. Suggest we reason how the torque on this coil compares with the torque in the original coil. Right? B will increase. Ferrous core increase the magnetic flux density B. Amplitude of torque increases. That's amplitude. Okay? This amplitude. Any comment?